Thank you. Just as a matter of introduction, I'm the HPC product manager for adaptive computing, and we've recently done some work for support of the Intel Phi in our products Moab and the open source product Torque. Just a little background for those who may not know, floating point accelerators have been around for a while. The first ones were FPGAs, field programmable gate arrays. These chips were basically general purpose hardware chips that were programmed after they were manufactured with some equations and so on to basically do some floating point calculations. After this little programming, the chips were set in what they could do, so there was no programmability after that. However, they were very useful for HPC type applications to accelerate simple floating point operations, and did that fairly well for their time. Later came along digital signal processors. These were purpose-built, specialized floating point processors that could be programmed. They had some limited software programmability and used by HPC to accelerate different types of floating point operations, some a little more complex. For instance, the Roadrunner cluster was built with IBM cell processors that had DSPs embedded in them. After that came general purpose graphics processing units. These were purpose built for very fast graphics processing, things like for video games and so on. These were totally programmable by software and used by HPC to accelerate complex type floating point applications. Then along has come, as has been announced yesterday, the Intel Xeon Phi, which is built on a MIC architecture. MIC stands for Many Integrated Cores, and like I just mentioned, MIC is an architecture, not an actual product. As an example, if you were to purchase a Victorian house, the architecture you've bought is Victorian, but the product you bought is a house. And the Intel Xeon Phi is the product that has the MIC architecture, which, like I mentioned, was announced yesterday by Intel. And so, even though it may have been referred to as the Intel MIC for a long time, that is the architecture and the products of Xeon Phi that customers purchase from Intel. Similarities between MIC architecture type devices and GPGPUs, they're both PCIe based devices. They can connect either via a plugging into a slot in like a motherboard or via a cable. An example of the cable is the NVIDIA Tesla S1070. It's a complete standalone system with a cable that plugs into a slot. Or you can have something that plugs directly into the slot itself, the example being an Intel Xeon Phi, and there's a Tesla also that matches that. It is a card that plugs in, has its own cooling and so on. And then also as a module that OEMs can use, system integrators can use and incorporate into HPC compute nodes. And there are models of both from both Intel and others that are available. Differences is the GPGPU type devices are purpose-built hardware. It is really not a general purpose processor like would power a PC or an HPC compute node. It has specialized software. It does not run a general purpose operating system and cannot run just normal jobs or programs. Therefore, to use HPC software on it, it requires some modification of the HPC software. For example, we have a customer, a U.S. national lab, who ported one of their large HPC applications. It took them 4 man-years to do it. They had to change some of the architecture internal to the program in order to adapt it to use with a GPGPU. With MIC architecture-based devices, it is purpose-built hardware, but the difference is that it's got an x86-based instruction set and therefore can run general-purpose software. For instance, Intel Xeon Phi systems run the Linux OS, and of course can run normal programs, just like any regular PC or HPC compute node that's x86 based. And the promise of these devices is that there will be a much smaller HPC software modification, man weeks, maybe months versus man years, as has been the experience of some customers. One of the big differences with the Intel mic architecture is that the technology is compiler driven, meaning that the compiler will look for parallelizable sections of code in the source code and will create code that can execute on the Intel Xeon Phi. To do this, it creates two binary files, one for an Intel Xeon processor and one for the Xeon Phi processor. The Xeon file will execute, it's the main program, it executes serial code, and the Phi binary file executes the parallel code. The way the program executes is it starts up on the Xeon processor, it goes and detects the presence of a Xeon Phi, and then starts up the parallel program file, the image file on the Xeon Phi board. And then the compiler has generated code that when it executes serial code, it executes it on the Xeon processor. When it reaches parallelizable code, it sends data and switches over to the code in the program running on the Xeon Phi and runs the parallel code there, and then sends the data, the results, back to the main memory of the Xeon. The anticipated benefits of this approach are far fewer man hours to code HPC parallel programs. You don't have to completely re-architect your program to take advantage of the parallelization. Also, it's not a bullet point here, but if there is no Xeon Phi available, the main program compiled for the Xeon does execute the parallel code, but of course in a serial manner. This is just a little animation about how this works between the two processors in a compute node, controlling transferring control back and forth between the two processors. Then, of course, ending the programs. What we have done in our Moab product and also the open source Torque product is added support for Intel mic-based architecture devices. For instance, Torque, we have added automatic detection of mic devices, so administrators do not have to manually configure these devices. Torque's pbsmom, that's the agent that runs on every compute node. When the node boots up, checks for the presence of mic-type devices, and when it finds any, reports them to the Torque server. And then the Torque server reports them to the Moab scheduler and workload manager. This is how the scheduler learns about the Intel Xeon Phis, and then they're making them available for scheduling by user jobs. Users then submit jobs requesting these resources. We have generalized, as you can see in these Moab job submission commands, we have generalized the naming of these type of devices after the architecture, not the product name. The first example requests 200 compute nodes with one Xeon Phi per node, whereas the second command asks for 200 compute nodes but asks for 10 Xeon Phis for the entire job, not per compute node. Moab fulfills this request, allocating the required resources, and tells Torque how many mic resources there are for the jobs, and if they're per node, which nodes have the mics, and so on. Torque then allocates the mic-based devices to a job, and where the job can use those devices. If there's more than one Xeon Phi per node, it's Torque's responsibility to allocate one of the Phis to the job, so that if the job is sharing or excuse me, if the node is sharing jobs being used by multiple jobs, and they each want Xeon Phis, then it will allocate them and inform the jobs of which one they have. There are metrics that Xeon Phi generates that Torque periodically polls and reports up to our Moab scheduler and workload manager product. These can be recorded in a database. They can also be used for scheduling policies. For instance, if the load is really heavy on a node with a Xeon Phi there, then that node can be avoided and other nodes can be used instead in order to not overwhelm a Phi with multiple jobs and so on. You can see from the list there information that's reported. Things like the number of cores or the number of threads can be used by an application to discover how many cores and how many threads there are, and then go ahead and do internal alterations of the job tasks to take advantage of those. Also how much memory is available and so on. This is an example of some statistics, or not statistics, but the metrics reported for the Intel Xeon Phis. This example actually comes from that box right there that I captured this morning, and there it contains 2 Xeon Phis inside of it, and you can see them both here reported as 2 mic-based architecture devices, and with mic 1 and mic 0, and then all of their metrics after them. And so this information can be recorded in a database along, tagged with the job and so on, and with the nodes that it executes on, so that people can analyze the jobs afterward if they desire. Benefits are that Moab automatically learns about the Intel Xeon Phis and other accelerators such as GPGPUs via Torque's node update report, and this gives it the ability to automatically learn about these devices and be able to schedule them as resources. Torque has been enhanced to automatically detect Intel Xeon Phi devices, so an administrator never has to manually configure these. They're just automatically detected when the system boots up, and it reports those to Moab and allocates them when the jobs are actually placed on a compute node and actually run. And any questions about any of this? Yes, sir. This will come out in Moab 7.2, which will release this month. Okay. We have been part of the Intel Mic beta program, and actually are working with a customer who has the first SGI, and oh, there they are right there in front of me. SGI's new UV2000, their very first customer, the University of Cambridge, Cosmos, is getting the first system, SGI UV2000, with Intel Phis. And we're working with SGI to does Moab reserve the CPU cores in the Phi? Is that the question? Yes, Moab runs on that, and it's very noisy.
For the Moab, is reserve the CPU cores or reserve the whole circuit? 8 cores. One the socket has the.
Oh, in the socket, yes.
To reserve the socket or reserve the cores?
The way the SGI is set up, each socket can be a NUMA node, okay, or the blade can be the NUMA node. And Moab and Torque operate with however they want to define the NUMA node, and then the NUMA node is the resource that is scheduled. So it's either the socket or the blade. And when Torque discovers the mics, we know which socket that is paired with, and so schedule those resources accordingly. So.